Chapter 14, Inference about the model. A residual plot is a scatter plot of the regression residuals against the explanatory variable. They help us assess the fit of a regression line. They estimate how much y varies about the true line. Outlier is an observation that lies outside the overall pattern of the other observations. The slope b and intercept of the least squares regression line are statistics. Calculated from the sample data, they are estimates of the unknown parameters. Parameters are slope beta and alpha intercept calculated from the population. Y hat is the notation to remind ourselves that the regression line gives predictions. R squared is the coefficient of determination, fraction of the variation in the values of mu that is explained by a least squares regression of y on x. Conditions for regression inference. There are a few things we need to keep in mind when we're doing regression inference. First of all, the standard deviation of y is the same for all values of x, and the value of sigma is unknown. Standard deviation describes the variability of the response y about the true regression line. Because sigma is the standard deviation of responses about the true regression line, we estimate it by a sample standard deviation of the residuals. Since we also observe two variables rather than one, n minus 2 is the degrees of freedom. The standard error about the line is this. For our first example, crying in IQ. Infants who cry easily may be more easily stimulated than others, and this may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. Table 14.1 contains data on 38 infants. So here, the crying is the x value, and the IQ is the y value. The equation of least squares regression line is this. Table 14.1 shows that the first infant studied had 10 crying peaks and a later IQ of 87. Now we'll calculate the predicted IQ for x equals 10. In order to do that, you plug in 10 for x in the equation for the least squares regression. And when we do that, we get a value of 106.2. To find the residual for the observation, we have to do the observed minus the predicted. The observed value is 87 for the IQ, and we minus the predicted value from it, which you calculated earlier for x equals 10 is 106.2. When we do that, we get a negative residual value of 19.2. When we repeat this calculation 37 more times, once for each subject, the 38 residuals are in the table as follows. Please take a moment to read these residuals and understand how these are calculated. Now we will calculate the variance about the line. The variance about the line is s squared equals 1 over n minus 2 and the sum of the residuals squared. So to do that, we have to do 1 over 38 minus 2 times the sum of the residuals squared. So our first residual was negative 19.2, and then you square it, and you add the next residual to it, which is negative 31.13 squared, and you go so on. When we did this, the sum of the residual squared was 11.032, and you multiply this by 1 over 36, and the answer is 306.26. Now the standard error is s to square root of s squared. So what we have to do is 306.26 square root, which equals 17.50. Here's a quick technology tip. In your TI 83 or 84, enter your x and y values in list 1 and list 2 and perform the least square regression. The calculator updates the list name resid and store resid in a list to find the one variable stats of the residuals. Then, divide the sum of x squared by n minus 2 to get s squared, the estimator of sigma. Confidence intervals for regression slope. The slope of the true regression line is usually the most important parameter in a regression problem. The confidence interval shows how accurate the estimate is likely to be. The confidence interval for beta has the form estimate plus or minus t star. T is the critical value times the standard error of b. Confidence interval for regression slope. Here is the equation for the standard error of b. Figure 14.4 shows the basic output for the crying study from regression command in the Minitab software package. Most statistical software provides similar output. Minitab, like other software, produces more than this basic output. When you use software, just ignore the parts you don't need. The first line gives the equation of the least squares regression line. The slope and the intercept are rounded off there. So look in the coefficient column of the table that follows for more accurate values. The intercept 91.268 appears in the constant row. The slope b 1.4929 appears in the cry count when we enter the data. The next column out of the output headed standard deviation gives standard errors. In particular, standard error of b is 0.4870. The standard error about the line is 17.50, and it appears to be below the table. There are 38 data points, so the degrees of freedom is n minus 2, so the degrees of freedom will be 38 minus 2, which is 36. For a 90% confidence interval for the true slope b, we will use critical value 2.042. So to get the confidence interval, we do b plus or minus t star times the standard error of b. The estimated b slope is 1.49 plus or minus the critical value with 36 degrees of freedom times the standard error of b, as we saw was 0.4870. And the confidence interval we get is 0.4985 to 2.4873. This interval tells us that we're 95% confident that the mean IQ increases by between about 0.5 and 2.5 points for each additional peak in crying. Please pause and take a minute to read this regression analysis. We will next discuss testing the hypothesis for no linear relationship. Here, the null hypothesis will be b equals 0. A regression line with slope 0 is horizontal. The mean of y does not change at all when x changes. This means that the null hypothesis is saying that there is no true linear relationship between x and y. The null also says that there is no correlation between x and y in the population from which we drew out the data. You can also use the test for zero slope to test the hypothesis of zero correlation between any two quantitative variables. The test statistic is just the standardized version of the least squares slope b. Example 3. For our next example, we will be testing the blood alcohol content data. The regression equation for this is as follows. It's on the top of the Minitab outlet. We can test the hypothesis that the number of beers has no effect on blood alcohol versus the one-sided alternative that more beers increase blood alcohol content. The hypotheses are the slope is 0, and the other alternative hypothesis is the slope is greater than 0. That means that more beers increases the blood alcohol content. When we do the test, it is no surprise that the test statistic is 7.8. And with the two-sided p-value of 0.00. This means that there is enough evidence to reject the null and conclude that the more beers increase blood alcohol content. The one-sided p-value is half this value. So it is also close to 0. Check that the t is the slope b 0.17964 divided by the standard error b 0.0024. So t equals b over standard error of b. And this is 0.00796 over 0.0024. And we get 7.48. The p-value is close to 0. Here's a quick technology tip to do a linear regression test. You can use a TI-84 to perform this test. Enter the x values scrying into L1 and the y values of IQ into L2. And you go to lin regression t-test, and in your screen enter L1 for x list and L2 for the y list, and state your null, whether it's does not equal to 0, less than 0, or greater than 0. This regression t-test results take two screens. The first screen reports that the t-statistic is 3.07 with degrees of freedom 36. The p-value is 0.4. And the slope is 1.429. And then you can get the standard error about the line. So here, according to our results, we have sufficient evidence to reject the null. When we do significant tests for regression slope, this is the equation we use. We will move into checking regression conditions, which are very important when we're doing a linear regression test. First of all, we need to make sure that the observations are independent. Repeated observations on the same individual are not allowed. The true relationship should also be linear. You should look for overall linear pattern. This could be through a residual plot, or check the linear regression or R value. The standard deviation of the response about the true line is the same everywhere. The scatter of the data points about the line should be roughly the same over the entire range of the data. You can test this by plotting the residuals. When you plot the residuals, you should make sure that the data points are scattered and there is no evident pattern in the display of the residuals. Another thing you should make sure is that the response varies normally about the true regression line. Make a histogram or a stem plot of the residuals and check for clear skewness or other major departures from normality. Like the other T procedures, inference for regression is not very sensitive to minor lack of normality, especially when we have many observations. The exception is the prediction interval for a single response Y. The end. Thank you for watching.